use a group of statistical methods and related to that joint probability methods. And we'll finish with Brisbane River Catchment flood study, how you're going to apply these methods in the study.
Ferdinand, why don't we try plan B if we don't have a rule?
You just actually apply them?
Yeah.
No turn.
Yeah, sure.
It's fuzzy, sorry folks.
Try that.
Okay. So Brisbane River Catchment flood study, we will discuss, like, let's say, these kind of methods, how we apply them. But I'm going to start with a spoiler alert. I'm not going to present results. So those of you who come here to discuss the results, please stay. But, the results are not available yet. Soon to come. And I think Conor will explain about the timeline. So statistical methods, joint probability methods. I'm sure there are some people here who have some experience with that. I'm sure there's also a lot of people who would like to stay away from those methods as far as possible. So the challenge for me is to kind of cater to both, and I hope that works out well. If not, if it's too difficult or unclear, please let me know. So, like I said, we start with flood risk. And flood risk management. So, risk, what is that? There are many definitions. This is the one that in current literature is mostly used. So, risk consisting of three components: hazard, exposure, and vulnerability. And hazard means probability that a flood occurs, and also the consequence in terms of flooded area, also flood depth, velocities, etc. Exposure is essentially the amount of people living in floodplains, but also the valuable assets. And vulnerability is how well are they protected? Do people have good evacuation plans? Are there good warning systems? Are the assets well protected? So those are kind of three options for the flood risk management to kind of reduce the risk. But reducing the risk, that's one of the main challenges, because that's what we want, and preferably within the budgets that are available. So some background on how we deal with this in the Netherlands. Later on we will move back to Australia, apparently. So the Netherlands, over there in Western Europe, and here you see a map of the flood-prone areas in the Netherlands. Dark blue is the area that is below sea level, and then I mean below mean sea level. So you can imagine how vulnerable these areas are. And in light blue are the areas that are above mean sea level, but still very flood-prone, because they are below high sea levels. So if there is a high storm surge, or if there's a high river discharge, these areas are also on the risk. So you can imagine that flood risk management and is high on the agenda in the Netherlands, as well as here. For this reason, because we have all these flood-prone areas, we got several measures to protect us from floods. Most famously are levees, or dikes as we call them, but also dunes and barriers, as you can see over here. These things are very costly to design, to construct, but also to maintain. So, what you look for is kind of a balance. So the benefit of these protection measures versus the costs. And this is let's say, the simplest picture that you're going to have. So you look for a certain level of protection, and you can imagine that the higher the level of protection, the more you need to invest. It's a nice straight line in this figure, that doesn't necessarily need to be, but this is just conceptual. And of course, if you increase the level of protection, the damages that you expect will decrease. The number of floods, the flood frequency will decrease. What you then get is two types of costs, and if you take the sum of the two, you get the blue line, the total cost. The cost of investment and the cost of the damages due to flood. And most likely there will be some sort of optimum in between. And that's generally the basis for how we design these structures, these flood defenses. But it's a bit more complex than that, because this is just talking about costs. But it's not just about money. Floods is also, of course, about lives, people, casualties. So we also analyze like what are, let's say if you look for an individual, what is the probability that in a given year that person may become a casualty of a flood event. These are the numbers that have recently been derived. Very small probabilities. These are checked against, let's say, what the probabilities that are more or less acceptable. Of course, you want to have them as low as possible, but it can be equal to zero, so you compare them to other risks like airplane crashes or industrial disasters. So our flood protections need to be such that these probabilities are below a certain level. So you have the combination of the two, costs and protection of lives, and in the Netherlands that results in safety standards. So they form the basis of our design of the levies. And as you can see on the left, these safety standards, these protection levels are expressed in terms of a probability, an annual probability. So what it means, on top you see 1 in 100, most of you probably know what that means. So the levy needs to be such that the probability of a big flood occurring needs to be 1 in 100 or lower. Preferably lower, but 1 in 100 is for those levies the aim. So that's how it works. Okay, this is essentially the basis for my talk today because these are probabilities, that's what we need to live up to. But then of course the next question is how do you determine these probabilities? And why are we even talking in terms of probabilities? That is because, it's one thing I forgot to mention is that these are protection levels, and for our existing levies, every 6 years we have an assessment to see if they still fulfill this requirement. So probabilities, why is that? Well, that's because we are dealing with a lot of uncertainties. And there are actually various sources. The main one is that we have natural variability. And so suppose we look at the river discharge, this is typically a graph of the river discharge with high peaks and then low flows in between. You already see that there is natural variability. That also means that we don't know when the next flood will be. We also don't know when that happens, what will be the extent of the flood, the magnitude. So that is the uncertainty related to the natural variability. But there are other sources of uncertainty. Because when we assess these probabilities related to the natural variability, we need to gather information. We need to have measurements of rainfall data, of flow data. We may even need to apply models to have our estimates available at locations for which we don't have measurements. But all these things have uncertainties in them. Even a process that seems to be simple like rainfall, and you just put a bucket outside essentially, and still you make some errors when you measure the actual quantity of that rainfall. And that is at the location where you have a measurement station. But there are a lot of locations where you don't have those, so you need to estimate those. So in other words, a lot of sources for uncertainty, and that is why whenever we talk about floods, we need quantify them in terms of probabilities. Today, we're going to essentially focus on one source of uncertainty, the natural variability, also because of the limited time. Now, how to quantify this? Well, one of the most straightforward and simple methods is to make a histogram. And this is an example that the numbers in the axis are perhaps a bit difficult to see, but essentially what you do is you define various ranges of potential outcomes. In this case, discharge. So, for instance, the range between 100 cubic meters per second and 200 cubic meters per second. And what you then do is simply, you have your series of measurements, and you simply count the number of times that the discharge was within that interval. And you do that for all intervals, also for 200 and 300 cubic meters per second, etc. So for each of these intervals, you get the number of times and the frequency of observations within that interval. And that really already gives a nice view of the natural variability and also of the probabilities involved. And you can imagine that this is the range where most of the discharges occur. So if you walk to the river on a random day, the river discharge will most likely be within that range. But you can also see over here you have the higher discharges, extrudes, they have low probabilities, but of course those are the events that we are interested in. But this is a histogram. It already has a lot of information that you need for flood risk analysis. Quite often what has been done is when you have such a histogram, it's kind of a table of numbers, but often convenient is people would like to use distribution function. And this example is the famous bell curve that you may remember, or may actually use every day. So this is just one example of how you can fit a distribution function through a histogram. This has the advantage that you then really have a mathematical description of the potential outcomes, in this case potential discharges in the river, and associated probabilities. Now, look. It's like there. Okay, so this is the outcome of, let's say, a very straightforward analysis. But what is the meaning? How valuable is this information? Because you can imagine this comes from a series of observations of perhaps 30 years of data. So what if we have another 30 years of data? Would we get more or less the same result, or would we get a completely different result? Well, in order to get a feel for how accurate this information is, I always like to look at examples where we already know the real outcome, and then see how the same techniques behave and what kind of information they provide. So you can, so I guess you all play games with dice. You can imagine you have a game with two dice, and you throw them, and you take the sum of the two, and that gives this outcome. So in green are the potential outcomes, 1 to 6 for both, and you take the sum of the two, and those values are given here in yellow. And you can see there's only one combination where you have the outcome 2, there's also one combination where you have 12, and there are several combinations where you have 7. So there are different outcomes and also with different probabilities. Now if you put that information in a histogram, this will be the result. And so on the left you have 2 and 12, relatively low probabilities, and 7 in the middle has a relatively high probability. So this is a histogram that shows the true results for this particular experiment situation. And this is relatively easy because we know how dice work, but suppose that the dice is as complex as Mother Nature, we say we don't know. So the only way to, let's say, obtain this kind of information is to do experiments, to start throwing the dice. So I did such an experiment. I had a long layover in Singapore, so what I did is I threw the dice 1,000 times. And I just counted the results, and what you get is the result is the histogram in green, and in yellow you see the results from previous slides, which is, let's say, the real outcome. And as you can see, well, the results are quite nicely close together, so yeah, this actually proves that if you do such experiments, if you have this kind of data, you can actually get a very good idea of the real probabilities. But what if I would have come from Sydney and I wouldn't have had a long layover, then I would have probably only been able to throw the dice 50 times. And then you get a result like this. And then you can see, you have quite significant differences between the real probabilities and the ones that I estimate from the data. So this already gives some idea about uncertainties. This is one source of uncertainty. If you always have, let's say, a limited data set. And it also gives an idea that better, if possible, try to get the data set that is as long as possible, because the more information you have, the more accurate your results are in general. However, if we look at flood risk analysis, we have the problem that we are mainly interested in the extreme events. So if we have a histogram, we might get very accurate estimates there in the middle. But now we want probabilities of events that maybe only been observed once or twice, or they are even maybe more extreme, they have never been observed. And still we need an estimate. So you can already imagine they have very limited data, and still you need an estimate, so the outcome will be uncertain no matter what. And we still need an estimate. So how do we do that? Well, that's a technique that is slightly different from deriving those histograms. So the way we do it is we first gather the information about the most extreme events in our series of observations. This is an example from the Netherlands, of course, the River Meuse, which has a catchment that is more than twice as large as the Brisbane River catchment. But the highest peak discharge is 3,000 cubic meters per second, which is much lower. And that's one of the advantages of living in a moderate Western European climate. That's a huge difference in the Brisbane River, smaller catchment, we get discharges of over 10,000 cubic meters per second. So what we do is we gather the information of the highest discharges and we start ranking them from high to low. And associated years, that's just additional information. In the next step, what we do is we come up with an initial estimate of the probability. So here we have the highest discharge of 3,175. And this comes from a series of about 100 years of observations. So the relatively straightforward reasoning is that, okay, this discharge has happened only once in 100 years. So our best estimate of the exceedance probability of this given discharge is 1 in 100. And then we do the same for number 2 on the list. So that discharge has been exceeded 2 times in 100 years. So our best estimate is that the probability is 2 times in 100. Etc. etc. Now, what we can also then do is translate that initial probability estimate to what is called an average return interval. Most of you probably know that it's essentially 1 divided by this one. So, probability of 1 in 100 then translates to a 100-year return interval. Then the next step is we put it in a graph to see how these numbers line up. So here you have these large events, the top 3, and so on. And what you see here on this axis is this return interval. So it goes up to 100 years in this example. And we plot this on a logarithmic scale. And it means that the numbers, they multiply by a factor of 10 each step. So 1,000 years. And on this axis, the vertical axis, we just show the numbers. And in this case, what you see, it's more or less, the result is more or less a line. I mean, it's not exactly a line because that would be really suspicious, but if you have a very thick marker, you might be able to draw lines. So, why not just do that? So what shows up as a straight line here on this logarithmic scale is actually the Gumbel distribution function. And it's one of the statistical distribution functions that is often used in this kind of analysis. And for this particular example, that gives a reasonable fit to the data, as you can see. But also, especially in the top end, there are some differences. So there's always some discussion of what is a good fit and what is not. But that would take more than you do this evening. So for now, hopefully you can accept that this is a reasonable fit. So what we then have is this dark line is a functional description, and the big advantage of that we can also that we can continue this line. That means that even though we have a series of 100 years, we can also come up with estimates for instance, 1,000-year average return interval. So that's the main reason why we like to fit distribution functions. And that is, well, we have seen the probabilities earlier, the safety regulations in the Netherlands. We often need those estimates for 1 in 1,000 years, even 1 in 10,000 years. Well, this is the way to do it. So fit the distribution function and extrapolate. Now that's all nice, but yeah, there are some disadvantages with that. One thing is that I told earlier with the example of throwing the dice that the longer your series is, the better. But that is only the case if your series is homogeneous. And the best example I can give is a series that I worked with in Egypt for the River Nile. And what you see here is discharges. You see every year you have a distinct wet season and dry season. So what you also see is that the construction of a big dam, Aswan Dam, totally changed the flows downstream. That makes sense. But can also imagine that if you start deriving statistics from observations, and you would do that for the whole series, that would totally give the wrong information, let's say for this point in time. So in this case, you would only derive the statistics from the subject of the series, because everything before that is sort of meaningless if you only look at the resulting flows. So that is a big disadvantage of this approach. You need this homogeneous series, and you don't always have that. So for that reason, we have alternative approaches, where we not only do statistical techniques, but we also use models. In this case, hydrological models that describe the processes in the catchment area. And what we then do is we start doing our statistics on the rainfall, put the rainfall in the hydrological model, and discharges come out of it. And there's different ways of doing that. One of the approaches is called the design event approach.